Imagine a time before gravity existed. This audiobook is your guide to understanding the origin of one of the cosmos's most essential forces, the very power that holds galaxies together and anchors you to the Earth. Did gravity simply appear as an inherent quality of space, or was it born at a distinct point in the universe's timeline? The answers we have, and the questions that persist, could fundamentally alter how you see reality. Gravity is far more than an abstract scientific idea. It is the force that physically grounds you in the world. With every leap you take, you experience its immediate tug, a sensation of the planet pulling you back. But have you ever paused to think about how this same force orchestrates everything around us? It dictates the rhythm of ocean tides, guides trees in their reach for the sky, and even ensures our hearts beat in unison with the cosmic pulse. Any conversation about gravity must include the monumental figure of Isaac Newton. The story of the falling apple represents much more than a simple trigger for his law of universal gravitation. It marked the beginning of a whole new way of thinking. What made his breakthrough so transformative was its simplicity. Newton articulated gravity not as some unpredictable natural whim, but as a consistent, understandable principle that governs the entire universe. However, our exploration of gravity certainly doesn't conclude with Newton. The journey of science brought us to Albert Einstein, a visionary who wasn't afraid to overturn conventional wisdom. His general theory of relativity didn't just redefine our view of gravity. It revealed that space and time are fundamentally intertwined. It makes you wonder how something so ordinary can be woven into a concept so profound. What's truly astonishing is that gravity doesn't just act on large bodies. Its reach extends to every particle in existence. Picture the very fabric of space-time warping and curving under its influence. While this concept is complex, it's our best tool for grasping phenomena like black holes, those enigmatic cosmic voids that push the limits of our understanding. The question of what actually occurs inside a black hole, however, remains one of science's greatest unsolved puzzles. In our own solar system, gravity is the master conductor. Every planet, moon, and asteroid engages in an immense cosmic ballet, their orbits dictated by this invisible force. Have you ever imagined what your life would be like on a world with a different gravitational pull? Your entire physical experience would be radically different, whether you were in a place where you felt as light as a feather or twice as heavy as you do on Earth. Beyond just affecting our bodies, gravity is a critical factor in the potential for life to arise on other worlds. As you look beyond our planet, you realize gravity's influence is even more profound, shaping the very architecture of the cosmos. Galaxies themselves are formed and sculpted by the gravitational interplay among their stars and gases. This force is so fundamental that without it, the universe as we observe it could never have come to be. This cosmic picture is complicated by dark energy, the mysterious entity that appears to be speeding up the universe's expansion. Gravity and dark energy are locked in a celestial tug-of-war, a dynamic that we are only just beginning to comprehend. Our attempts to understand this balance are pushing the boundaries of what we know about the universe's ultimate fate. Throughout this journey, scientific verification has been essential for cementing our theories about gravity. For centuries, countless experiments, ranging from the straightforward to the incredibly sophisticated, have put our ideas to the test. For instance, watching objects fall in a vacuum proves that gravity pulls on everything equally, no matter its mass. Today, the frontier has moved to the quantum realm, as we design new experiments to probe gravity's nature at the smallest scales. Our understanding of gravity has also become deeply integrated into modern technology. Without it, the Global Positioning System, or GPS, and the satellites that power it, tools that have reshaped modern life, would be impossible. The signals that make your phone work must precisely account for gravity's effects on time. These technological marvels stand as a powerful testament to gravity's pervasive influence on our daily activities. Here on Earth, gravity has been a pivotal force in life's evolution. Everything from the direction rivers flow to the very air in our atmosphere is a consequence of its constant pull. This raises a compelling question. How does gravity impact the chances for life on other planets? The ongoing search for habitable worlds is deeply tied to finding a place where gravity is just right. Over the centuries, a number of myths and popular fallacies about gravity have taken hold. These common misunderstandings can distort how this force actually operates. Correcting these ideas isn't just a matter of academic accuracy. It allows you to perceive the world around you with greater clarity and appreciation for its underlying laws. As we look toward the future, the investigation of gravity continues to be a vibrant and expanding area of science. New theories and experiments are constantly being developed, with each breakthrough bringing you closer to a complete picture of this foundational force. Gravity is anything but a closed chapter in physics. It remains a frontier rich with potential discoveries and profound mysteries waiting to be solved. To contemplate gravity is, in a way, to contemplate your own position within the cosmos. This ever-present force is a daily reminder of your connection to everything else in the universe. From a child tossing a ball into the air to the slow formation of a new galaxy, gravity is the unifying thread that holds our magnificent reality together. So, the next time you gaze up at the night sky, take a moment to remember that every star you see is held in place by this silent, powerful force. The story of gravity is a remarkable saga that spans human history, from the earliest observations of our ancestors to the sophisticated theories now tackling the universe's deepest secrets. It's hard to find anyone who hasn't wondered why things fall down or how the planets stay in their orbits. Humanity has been pursuing these fundamental answers since antiquity, with each new insight serving as another rung on the great ladder of knowledge. In ancient times, civilizations like the Greeks and Egyptians were already speculating about the essence of gravity. Philosophers such as Aristotle proposed that objects were simply drawn toward the center of the earth as part of their intrinsic nature. While this was an intuitive explanation for its time, it represented a very limited perspective on a much grander cosmic principle. So, how did we advance from these preliminary notions to a more profound understanding? The journey takes us to the Renaissance, an era that sparked a revival in scientific inquiry. A pivotal moment occurred in the 17th century when a young Isaac Newton began to formulate his concepts of gravity. But what was it that led him to identify this unseen force that appears to direct everything in our world? Newton noticed a parallel between apples dropping from trees and the moon's continuous orbit around the Earth, suspecting a connection between these two seemingly separate events. In 1687, he put forward the idea that an inherent force pulls all objects toward one another. This concept evolved into the law of universal gravitation, a truly transformative proposition for its time. Newton's law was nothing short of revolutionary. You can envision an invisible cord linking every object in the cosmos, a cord that grows tighter as the masses of two objects draw closer. This perspective didn't just alter the course of physics, it completely reshaped how we perceive the universe. However, what were the boundaries of this incredible law? For all its success, Newton's theory was unable to account for specific observations, such as the unusual orbit of Mercury, or the way starlight bends when it travels near the sun. These inconsistencies highlighted the need for a more comprehensive explanation. Thus, at the start of the 20th century, the brilliant physicist Albert Einstein took on the monumental task of challenging the established scientific consensus. With his theory of general relativity, Einstein introduced an entirely new way to think about gravity, not as a force pulling objects, but as the very curvature of space and time. Have you ever considered that space itself might be like a flexible fabric, warping under the influence of heavy objects? This is precisely what Einstein suggested, and his theory was a major breakthrough. Imagine you place a heavy bowling ball onto a trampoline. The surface sinks, forming a well that naturally draws smaller items toward it. This analogy captures the essence of Einstein's proposal. His theory not only provided explanations for phenomena that Newton's could not, but also unlocked a much deeper comprehension of the cosmos itself. According to Einstein's revolutionary ideas, gravity's influence extends beyond celestial bodies to affect time itself. In the vicinity of an incredibly massive object, such as a black hole, time actually passes more slowly. A truly staggering concept. The theories of both Newton and Einstein are far from being just historical artifacts. They continue to find practical application in our modern technology. Yet, the narrative of gravity doesn't conclude with Einstein. As we venture into the age of quantum physics, we encounter new and fascinating questions. For example, how does gravity interact with the fundamental forces that operate at the subatomic level? This enigma has spurred scientists to investigate new theories and conduct innovative experiments. Contemplating the history of our study of gravity, it's impossible not to speculate about what discoveries lie ahead. Current research is focused on unifying general relativity with quantum mechanics. Is it possible that a single, elegant theory could explain all the fundamental forces of the universe? The prospect of one day achieving a complete understanding of gravity remains a powerful motivation for scientists around the globe. Furthermore, the history of gravity is defined by the critical experiments that validated the theories of both Newton and Einstein. From Galileo's renowned experiments with falling bodies to the observation of starlight bending due to the sun's gravity, these experimental proofs have been essential to building our current knowledge. One can only wonder how many more breakthroughs are waiting to be made. From Aristotle's initial musings to Einstein's intricate frameworks, the pursuit of knowledge about this fundamental force has remained a persistent theme throughout human history. The law of universal gravitation, which Isaac Newton formulated in 1687, stands as a cornerstone of physics, giving us the tools to comprehend how objects interact across the universe. To really understand what Newton's law implies, let's think about two objects, such as an apple and our own planet. The apple's fall to the ground isn't just an isolated event. It's the result of a mutual attraction between them. Newton taught us that this pulling force is governed by two factors, the mass of the objects and the distance separating them. The greater the mass, the more powerful the attraction, while greater distance results in a weaker force. Why does this law hold such immense importance? Trying to solve a complex puzzle without the essential pieces is a futile exercise. The law of universal gravitation provided humanity with a solid basis for understanding movement, both on Earth and in the heavens. It enabled us to predict the trajectories of planets and stars, and was even instrumental in launching spacecraft to explore beyond our world. However, it became clear over time that the law of universal gravitation had its limits and raised perplexing questions. How could a force exert its influence across the pure vacuum of space? This was a puzzle that confounded many scientists. While Newton's law successfully described a wide array of phenomena, it couldn't clarify everything, especially as astronomical observations grew more precise. This is where Albert Einstein's general theory of relativity, unveiled in 1915, profoundly altered our perception of gravity. He argued that gravity isn't a force at all, but rather the curvature of space-time created by the presence of mass. As mentioned, if you put a bowling ball on a trampoline, its weight causes the fabric to bend, creating a dip that makes smaller objects roll toward it. This is analogous to how gravity operates on a cosmic scale. Within this new understanding, planets don't simply circle the sun because of a pulling force. Instead, they are following the most direct path available to them through a space-time that has been warped by the sun's immense mass. This leads to a captivating question. If gravity is the result of space-time curvature, how can we actually observe and measure its effects? Each discovery, from Galileo's foundational free-fall experiments to precise observations of Mercury's orbit, has added another vital piece to the gravity puzzle. Newton's law of universal gravitation, while fundamental, represents just one chapter in a much larger narrative. A perfect modern example of this is the detection of gravitational waves, which Einstein predicted, and which have now been confirmed by recent astronomical observations, continuing this thrilling scientific adventure. Gravity is a fundamental force that is with us every single moment of our lives. But have you ever stopped to consider its place within the broader landscape of classical physics? To truly grasp gravity in this context, it's necessary to travel back in time and examine how the scientists of previous centuries integrated this phenomenon into their comprehensive theories of the world. Imagine an era when the forces that dictate the movement of objects were a complete enigma. For centuries, thinkers and philosophers posed the question, why do objects fall? The pursuit of an answer was relentless, from Aristotle, who theorized that an object's falling speed was determined by its weight, to Galileo, whose experiments with spheres of varying masses challenged this long-held belief and demonstrated that, in a vacuum, all objects descend at the same rate. It was Isaac Newton, in the 17th century, who provided the revolutionary answer. He didn't just ponder why things fall to the ground. He took the audacious step of asking why the moon remains locked in orbit around the Earth instead of flying off into space. This profound curiosity guided him to formulate the law of universal gravitation, which posits that every object in the universe attracts every other object with a force directly proportional to their masses and inversely proportional to the square of the distance separating them. Newton's law did more than just reshape our comprehension of gravity. It established the very bedrock of classical physics. Within this new paradigm, gravity was no longer an isolated idea, but was intricately woven together with the other forces and laws of motion. You can think of it as a keystone in an arch. Gravity was the central piece that locked all other physical principles into a stable, cohesive structure. But what occurs when the circumstances become extreme, such as when objects travel at velocities nearing the speed of light, or within the influence of incredibly powerful gravitational fields? It is in these scenarios that the boundaries of Newtonian physics start to become apparent. Although Newton's model could brilliantly explain a vast array of phenomena, it was unable to accurately describe these severe conditions, like those encountered in the depths of space, or concerning the fundamental nature of light itself. This discrepancy caused numerous scientists to question whether there was an aspect of gravity that simply couldn't be explained with the tools Newton had provided. In classical physics, gravity was conceptualized as a force that acted instantaneously across a distance. Imagine tossing a ball upward. The instant it pauses at its peak and starts to descend, you are observing this gravitational force in action. To Newton, this force acted like an unseen tether linking the Earth and the ball, a connection that felt almost magical in its nature. Over time, however, the perceived magic of gravity gave way to a deeper complexity, and as scientific investigations pressed forward, the necessity for a theory that could transcend Newton's limitations became undeniable. This was the pivotal moment when the field of physics arrived at a crossroads, standing between its classical past and its modern future. Einstein's theory of relativity would soon arrive to completely upend everything that was previously understood about the force of gravity. Before we explore that shift, it's vital to appreciate just how profoundly Newton's perspective shaped the course of science. Classical physics, with his laws at its core, provided a coherent framework for making sense of the universe, and its influence extended far beyond gravity into fields like engineering and astronomy. And yet, for all its triumphs, scientists came to see that gravity, while fundamental, was merely one component of a much grander and more intricate puzzle. Have you ever considered why, after all of our scientific progress, gravity continues to be such an intense area of study? The reason is rooted in its inherent intricacy. While Newton delivered an incredibly effective model, the true essence of gravity is far more subtle than it seems on the surface. Each new experiment and observation tends to unlock doorways to entirely new questions and mysteries, reminding us that scientific understanding is a constantly evolving journey. Consider the ability to detect gravitational waves, ripples in space-time generated by cataclysmic cosmic events like the merging of two black holes. These observations offer further evidence that gravity is a far more intricate phenomenon than we once imagined. This brings us to another pressing question. What is the relationship between gravity and dark energy, the enigmatic force driving the accelerated expansion of the universe? The interaction between gravity's pull and dark energy's push is a central debate in modern physics. Despite these new frontiers, Newton's law of universal gravitation continues to be an exceptionally useful tool. It enables us to plot the trajectories of satellites, forecast eclipses, and comprehend the movements of celestial bodies with astonishing precision. Its legacy is woven into the fabric of our daily technologies, from global positioning systems to the intricate designs of space exploration missions. The journey, however, is far from over. The quest to unify gravity with quantum mechanics, the theory that governs the bizarre behavior of subatomic particles, stands as one of the most formidable challenges in all of modern physics. This fundamental question of whether gravity, which appears so straightforward in our everyday experience, can be harmonized with the strange and counterintuitive rules of the quantum realm, opens an entirely new chapter in our exploration of the universe. Ultimately, the law of universal gravitation was more than just a scientific landmark. It laid the foundation for a much deeper comprehension of reality. It has served as our guide through centuries of discovery, consistently forcing us to challenge our perceptions of the cosmos. Our innate human curiosity about gravity shows no sign of diminishing. In fact, each new answer only sparks more questions, propelling us forward in our pursuit of knowledge. What astonishing revelations about gravity's role in the universe await us in the future? Only time will provide the answer. Gravity represents something far more profound than just a physical event. It stands as a testament to human inquisitiveness and our innate yearning to make sense of the cosmos. As you and I venture into the immense ocean of scientific understanding, gravity acts as a guiding light for researchers navigating the universe. While classical physics gave us essential frameworks, our journey toward fully grasping gravity has really only just started. The very questions that emerge from our studies propel us forward, serving as a reminder that the quest for knowledge is itself a compelling force, drawing us toward the great unknown. The force that keeps your feet on the ground and pulls apples toward the earth transforms into a much more complex idea when you delve into Albert Einstein's theory of general relativity. So what exactly did Einstein accomplish that so radically altered our view of gravity? The answer extends well beyond merely defining it as a force. It's rooted in how gravity fundamentally interacts with the very fabric of space and time. In classical physics, gravity was perceived as an invisible pull between objects. But in 1915, Einstein put forth a revolutionary notion. Gravity is not a force in the conventional sense, but is actually the bending of space-time. To help you picture this, imagine a large trampoline. If you place a heavy bowling ball in the middle, you can see how the material stretches and sags. Now, if you were to roll a marble close to that bowling ball, it wouldn't travel in a straight line, but would instead follow the curve created by the heavier object, possibly even circling it. Through this analogy, Einstein demonstrated that massive celestial bodies like stars and planets actually warp the fabric of space-time, and we perceive this distortion as the phenomenon of gravity. Curiosity, as you know, is a powerful motivator. If gravity is indeed a curvature, you might wonder why we don't perceive it differently as we move around the globe. This is where the intertwined nature of space and time becomes critical. The Earth's rotation and its orbit around the Sun generate an effect that consistently keeps us planted firmly on the surface. But what if you could journey to a black hole, a place where gravity reaches an extreme intensity? There, the bending of space-time would be so severe that time itself would perceptibly slow down, leading to a scenario where a single day spent near the black hole could correspond to 1,000 years passing back on Earth. Many people assume that gravity exerts a uniform pull across the entire universe, but its influence actually fluctuates. Einstein revealed that gravity affects not only physical objects but also light itself, a principle we call gravitational lensing. It is as though gravity has the ability to bend light rays around itself. Consequently, when you observe a distant cosmic object, the image you see might be warped by the gravitational influence of other massive bodies situated between you and it. In a way, gravity serves as a natural cosmic lens through which we can view the universe. Einstein's theory does more than just describe gravity's behavior. It also prompts us to ask even more captivating questions. Could gravity affect light in such a way that it allows us to detect objects that are otherwise invisible? The answer is a definitive yes. This very principle has enabled astronomers to identify entire galaxies and galactic clusters that would have otherwise gone completely unnoticed. Over the decades, general relativity has been subjected to numerous experimental verifications. The renowned solar eclipse experiment of 1919, for instance, proved that starlight does indeed bend as it passes by the sun, precisely as Einstein had foretold, marking a pivotal moment for his theory and ushering in a new age of physics. So how does all of this affect your daily life? Relativity is far from being just a lofty abstract idea. The very technology you use constantly, such as the Global Positioning System, or GPS, relies on its principles to function. Satellites in orbit around our planet must meticulously correct for the effects of both gravity and time dilation to transmit accurate location data. Without Einstein's profound insights into gravity, your GPS navigation would be hopelessly inaccurate and fundamentally unreliable. General relativity also encourages us to contemplate the universe on its grandest scale, providing a framework to understand cosmic events like the ongoing expansion of the universe and the enigmatic nature of black holes. What secrets do these phenomena conceal? Gravity is central to their formation and their dynamics, compelling us to ponder their ultimate significance. Einstein's exploration of gravity is a captivating story, but it is certainly not the final chapter. As scientists persist in probing the depths of space and time, new puzzles constantly emerge. One of the most significant of these is quantum gravity, which is a theoretical endeavor to merge general relativity with the principles of quantum mechanics. This is a burgeoning area of research that holds the potential to once again completely revolutionize our understanding of gravity. The influence of Einstein's relativity on the field of physics is difficult to overstate. It has unlocked the door to a vast number of new inquiries and theories that continually push the boundaries of our cosmic comprehension. At its very heart, gravity forms the essential bridge between the world you experience every day and the profound mysteries of the cosmos. When you reflect on this journey, it is truly staggering to consider how a simple thought about a falling apple could ultimately lead to uncovering the universe's most guarded secrets. Human curiosity, when coupled with the genius of minds like Einstein's, has empowered us to make monumental leaps in our understanding of gravity. This, in turn, deepens our understanding of ourselves and our position within this immense universe. The pursuit of knowledge is a never-ending cycle, where each solution reveals new questions, inspiring us to continue our exploration and learning. Gravity is a force that is perpetually active all around you. But have you ever stopped to think about how it shapes not just objects in free fall, but absolutely everything we observe in the cosmos? It is quite extraordinary to realize that gravity is not only the reason you stay on the Earth, but also the organizing principle that dictates how planets orbit the sun and how vast galaxies form and evolve over billions of years. How can a phenomenon that is completely invisible wield such a transformative power over the very structure of space and time? You can visualize gravity as a kind of immense, flexible sheet stretched out across the entire universe. If you were to set a heavy ball onto this sheet, its surface would warp and create a distinct indentation. This simple analogy provides a clear way to grasp how mass distorts the space that surrounds it. The more massive an object is, the more profound the depression it carves into this fabric. Consequently, when a smaller object such as a marble rolls near this dip, it is naturally guided toward the larger mass. In this conceptual model, the marble can represent a planet, while the heavy ball symbolizes a star like our sun. Let's take a moment to think about time itself. Are you aware that gravity actually influences our very perception of its passage? Picture two perfectly synchronized clocks, one resting on the surface of the Earth, and the other orbiting 1,000 kilometers overhead on a satellite. Upon the satellite's return, you would discover that its clock has ticked slightly ahead, a phenomenon known as gravitational time dilation. This occurs because time flows more slowly within a powerful gravitational field like Earth's than it does in a region where gravity's pull is weaker, almost as if gravity operates on its own unique timescale. Now, let's explore how gravity's influence extends beyond physical objects to affect light itself. Have you ever considered how it's possible for us to observe stars from the farthest reaches of the universe? The answer lies in gravity's ability to actually bend the path of light. As light from a distant star travels past a massive object like a galaxy, its trajectory is warped, which allows us to see stars that would normally be obscured from view. Astronomers call this effect gravitational lensing, and it has become an essential tool for studying the cosmos. Gravity is also the master architect of cosmic structures, playing a fundamental role in their formation. It is the binding force responsible for everything from the birth of stars within nebulae to the assembly of vast galaxy clusters. As interstellar gas and dust gather under gravity's persistent pull, they eventually collapse inward to ignite and form new stars. Without this essential force, our universe would be an unrecognizable void, devoid of the intricate and beautiful complexity we observe today. So what occurs when gravity reaches its most extreme potential? This leads us to the subject of black holes, regions in space where the gravitational pull is so immense that absolutely nothing, including light itself, can break free. While the concept might sound like pure science fiction, I assure you that black holes are entirely real. They are born when a truly massive star runs out of nuclear fuel and collapses under the sheer weight of its own gravity. This catastrophic event is one of the most spectacular processes in the cosmos, showcasing gravity's power to fundamentally reshape matter and energy. For centuries, scientists have investigated gravity from many different angles, but Albert Einstein's theory of general relativity marked a true paradigm shift. He put forward the revolutionary idea that gravity isn't a force at all, but rather a consequence of the curvature of space-time itself. In this model, massive objects don't exert an invisible pull on each other. Instead, they follow the curved pathways created in the fabric of space-time. This profound insight completely transformed our comprehension of gravity and unlocked entirely new avenues for scientific inquiry. In the field of cosmology, gravity holds some truly fascinating implications, particularly concerning the expansion of the universe. For a long time, the prevailing assumption was that the mutual gravitational attraction of all matter would gradually slow this expansion down. However, much to the astonishment of the scientific community, observations revealed that the universe's expansion is actually accelerating. This discovery led to the concept of dark energy, an enigmatic force that appears to counteract gravity and push the cosmos apart at an ever-increasing rate. Just try to picture a universe devoid of gravity. It would be a scene of utter chaos, with galaxies scattering and no recognizable structures able to form. Beyond its role in cosmic architecture, gravity is also a critical consideration in our search for life elsewhere. A planet's surface gravity is a fundamental factor in its ability to support life, as it determines conditions like the presence of liquid water and a stable atmosphere. This makes gravity a key component in the quest for extraterrestrial life, not just a subject of scientific interest. When you truly reflect on it, it becomes evident that gravity is far more than a simple pull between objects. It is an intrinsic element of the cosmic framework. This force governs everything, from the birth of stars to the final destiny of the universe itself. And it drives us to keep asking the fundamental question: how does it all work? Gravity's influence connects us to the cosmos in ways we are only beginning to grasp, with each new discovery bringing us a step closer to solving the profound mystery of existence. So the next time you gaze at the night sky, remember that gravity is the unseen force at the core of every star, planet, and galaxy, weaving the magnificent and intricate tapestry of our reality. The phenomenon of gravity has captivated human curiosity for as long as we have looked to the skies. But how can we be so sure of its existence? Throughout scientific history, brilliant minds have designed clever experiments to both understand its mechanics and validate the theories about it. Today, I want to walk you through some of those pivotal experiments, the very ones that not only proved gravity's reality, but also completely transformed our perspective on the universe. We can start with a truly classic example: Galileo's legendary experiment at the Leaning Tower of Pisa. As the story goes, he simultaneously dropped two spheres of different masses and sizes from the top. Now, what would you expect to happen? Would the heavier one plummet to the ground first? Contrary to the common belief of the time, both spheres struck the Earth at the exact same moment. This elegant demonstration proved that, without the interference of air resistance, every object accelerates downward at the same rate, delivering a decisive blow to the long-held Aristotelian idea that heavier items fall faster. Building on Galileo's work, Isaac Newton famously pondered a simple question: why does an apple fall down from a tree instead of floating upwards? This simple curiosity was the spark that led him to formulate his law of universal gravitation. To test his theory, Newton understood he had to look to the heavens, so he turned his telescope to the motion of the planets and the moon. He discovered that the very same force pulling the apple to the ground was also responsible for keeping the moon locked in its orbit around the Earth, a landmark realization that unified the laws of physics on our planet with those governing the entire cosmos. While Newton had brilliantly described how gravity worked, it wasn't until the late 1790s that anyone managed to actually measure its force in a laboratory. A scientist by the name of Henry Cavendish devised an incredibly sensitive experiment that allowed him to directly quantify the gravitational attraction between objects. This was a monumental achievement that moved the study of gravity from celestial observation to precise empirical science. With a remarkably clever apparatus, he determined the gravitational attraction between two lead spheres. You may be surprised to learn that this experiment did more than just validate Newton's law. It also enabled scientists to compute the very density of our planet. Using nothing more than a thread and some weights, Cavendish demonstrated that gravity is not merely a concept, but a tangible force that can be precisely measured and quantified. In the 1960s, a team of researchers undertook an even more fascinating experiment involving the free fall of a sphere within a vacuum. Picture a setting completely devoid of air, where friction has no effect at all. When they released a sphere alongside a lighter object, what do you suppose took place? They both plummeted to the ground in perfect unison, affirming the principle that gravity exerts an equal influence on all objects, irrespective of their characteristics. Another experiment that deserves attention is the oscillation of a pendulum. If you watch a pendulum swing, you'll observe that its movement is consistently regular and is not affected by its mass. But what is the underlying principle of this motion? By calculating the time required for the pendulum to complete a full swing, researchers gained deeper insights into the acceleration produced by gravity, revealing how this fundamental force governs both time and movement. Within the field of contemporary physics, experiments conducted in drop towers, which are laboratories designed for microgravity research, have unveiled new possibilities. By letting objects fall inside these towers, scientists can observe their behavior free from the main effects of gravity. This method has been instrumental in advancing our knowledge of how forces operate in space and how materials react in extreme environments. Of course, we must also consider the momentous detection of gravitational waves. The collision of two black holes produces ripples that travel across the fabric of space-time. It's remarkable to think that Einstein predicted these waves over a century ago, yet their first actual detection didn't occur until 2015. This discovery provided further validation for the theory of relativity and significantly deepened our comprehension of gravity. Numerous experiments have also focused on the behavior of falling objects on other planets. Just imagine attempting to perform a gravity experiment on Mars, where the gravitational pull is just 1/3 of what it is on Earth. Scientists have dispatched missions to measure how objects fall there, studying the ways in which a different gravitational field alters their motion. This research not only broadens our understanding of gravity, but is also vital for the future of humanity's journey into space. Then there are the ongoing gravity experiments in orbit, where astronauts aboard the International Space Station live and work in a state of microgravity. You've likely seen footage of them floating effortlessly. This captivating sight is more than just a novelty. It provides scientists with a unique opportunity to study how reduced gravity impacts the human body and other living organisms. Every one of these experiments has served as a critical piece in the puzzle of our understanding of gravity. It is through persistent curiosity and careful observation that we have managed to uncover many of the secrets of this foundational force. Gravity isn't just what anchors us to the Earth. It is the universal thread that weaves together planets, stars, and galaxies across the immense expanse of the cosmos. Science, by its very nature, relies on repetition and confirmation. Each experiment, from the most basic to the extraordinarily complex, has helped to reinforce our knowledge of gravity. As we persist in our explorations and devise new tests, human inquisitiveness will continue to drive us towards solving the universe's remaining mysteries, serving as a reminder that for all we have learned, there is so much more to uncover about this incredible force. The story of our study of gravity is truly a narrative of exploration, revelation, and an unending search to comprehend our own position in the universe. When you gaze at the night sky, you are looking out into a vast and enigmatic solar system, all of it orchestrated by a single primary force: gravity. Have you ever considered that this force not only holds our planet in orbit, but also choreographs the intricate dance of every celestial body, from giant gas planets to the smallest asteroids? Gravity is the cosmic glue that binds them all together. Let's begin right here on Earth. Our world is effectively a giant magnet, constantly pulling everything toward its core, a phenomenon we perceive as weight. But what if you could move a significant distance away? If you were to journey to the moon, where the gravity is only 1/6 as strong, a weight of 60 kilograms on Earth would feel like just 10 kilograms. Imagine how that would transform your ability to jump. It is precisely this gravitational force that keeps the moon locked in orbit, preventing it from wandering off into deep space. Planets like ours are in perpetual motion, and each one orbits a star. In our solar system, that star is the Sun. What prevents them from simply flying out of their orbital paths? The solution is gravity. The Sun's immense mass generates such a powerful gravitational field that it securely holds all the planets in their courses. It's as if the Sun is leading each planet in a celestial waltz, guiding it with an unseen force. This gravitational influence isn't limited to planets. Moons, which circle planets, are also bound by its pull. Take Jupiter's moon Europa, one of the most compelling objects in our solar system. It is constantly subjected to the gravitational forces of its colossal parent planet and other nearby bodies. These interactions cause Europa's surface to flex and stretch, a process that might be crucial to the possibility of life existing in an ocean beneath its icy shell. Now, let's consider asteroids. These small, rocky objects, mostly found in an orbit between Mars and Jupiter, are also actors in this grand cosmic play. The gravitational pull from neighboring planets can disrupt their trajectories, nudging them in different directions and occasionally sending them on a new path into the inner solar system. In a universe defined by constant movement, gravity functions as the ultimate director, orchestrating the journey of every object. Gravity's reach is also responsible for impressive phenomena right here at home, such as the ocean tides. The gravitational tug of both the moon and the sun constantly pulls on our planet's water, creating the rhythmic rise and fall of the sea. This serves as a daily reminder of the powerful, ever-present nature of this fundamental force. When you observe the rhythmic rise and fall of ocean tides, you are witnessing the direct effect of the moon's gravitational pull on our planet. This constant shifting of sea levels is far more than a beautiful natural occurrence. It fundamentally shapes marine life and dictates the fragile balance within coastal ecosystems. Even as you journey to the distant edges of our solar system, gravity's influence remains paramount. Here you will find Pluto and other dwarf planets, whose gravitational force, while modest compared to the gas giants, is still strong enough to command their own orbiting moons. This demonstrates that even smaller celestial bodies play an essential part in the grand cosmic design. Then you have the comets, those cosmic wanderers that travel from the solar system's most remote regions. As the sun's gravity draws them inward, their icy hearts heat up, releasing the gas and dust that form the breathtaking tails you can sometimes see in the night sky. In this way, gravity acts not just as an attractor but as a creative force, giving comets their dynamic and brilliant appearance. Our solar system also holds many enigmas, such as the strange orbits of certain bodies that defy conventional explanations. These trans-Neptunian objects, located beyond Neptune's path, interact gravitationally with other celestial masses, producing complex orbital dynamics that we are still working to comprehend. Looking beyond our own system, you find that the very stars of our Milky Way galaxy are bound together by this same fundamental force. The gravitational field of each star subtly influences its neighbors, maintaining a delicate equilibrium that assigns every sun its proper place in the galactic structure. As you zoom out even further, you see gravity as the master architect of the universe, clustering galaxies together and holding them in vast cosmic webs. Gravity also presents us with significant challenges and questions as we look toward the future of space exploration. Every mission you can imagine, from deploying rovers on Mars to sending satellites to observe distant worlds, must meticulously calculate its effects. The success of landing on other celestial bodies and navigating the void between them is entirely dependent on mastering this elemental force. Ultimately, gravity is not simply about masses pulling on one another. It is the fundamental conductor of our solar system's orchestra, choreographing the intricate movements of planets, moons, asteroids, and comets. Our universe would be an unrecognizable and chaotic place without it. To understand gravity is to hold one of the essential keys to unlocking the cosmos's greatest secrets, and one can only wonder what new insights this incredible force will reveal to us in the years to come. Today, we turn our attention to one of the most enthralling phenomena in the entire universe: black holes. These enigmatic objects have long sparked the curiosity of scientists and the public alike. But to truly grasp what they are and how they come into being, you first need to understand the fate of a massive star when it depletes its nuclear fuel. Picture a colossal sphere of gas and fire blazing in the cosmos. Once this star exhausts its energy reserves, its own gravity overwhelms it, causing the core to collapse in a spectacle that pushes the limits of our knowledge. Gravity, the very force that once held the star together in a stable balance, becomes the agent of its dramatic transformation. As this stellar collapse accelerates, gravity intensifies to an unimaginable degree, creating an object of such extreme density that its pull becomes inescapable, even for light. This is the birth of a black hole, a location in space where gravity reigns so supreme that nothing, once captured, can ever break free. But why are these cosmic objects so vital to our understanding of the universe? Black holes are far from being mere oddities. They are foundational to the universe's large-scale structure. For instance, you should know that a supermassive black hole is believed to reside at the center of nearly every galaxy, including our own Milky Way. Ours is named Sagittarius A star, and its mass is millions of times greater than our sun's, influencing not only the stars orbiting it, but also the very evolution of our galaxy. If black holes possess such immense power, you might ask why they are invisible to our eyes. The answer is rooted in their very essence. Their incredible density means they emit no light of their own. However, this doesn't prevent us from detecting their presence. Astronomers use clever, indirect methods, such as observing the erratic dance of stars that are being tugged by an unseen force. It is much like detecting a hidden magnet by watching how it affects metal objects around it. Black holes also have the astonishing capacity to consume matter. When a star or another object strays too close, it crosses the event horizon. a boundary from which there is no return. Think of it like a massive waterfall. If you drift past the edge, you are inevitably pulled down. Once anything passes a black hole's event horizon, it is irretrievably lost to the outside universe.
This leads to one of science's most profound questions. What happens to the matter that falls inside? Is it annihilated, or is it somehow transformed? Scientists are actively exploring this mystery. Some theories propose that matter is shredded into a flow of pure energy, while others suggest that the information it contains might be preserved within the black hole in some unknown way, sparking fascinating discussions about the fundamental nature of reality and quantum physics. Furthermore, black holes are dynamic entities that can merge, forming even more massive black holes in the process. Such a collision unleashes gravitational waves, which are ripples in the very fabric of space-time that our instruments can now detect. This incredible breakthrough has provided us with a new way to observe the cosmos, allowing us to listen to the echoes of cataclysmic events from across the universe. So, what does the existence of black holes imply for your understanding of space and time? In their immediate vicinity, time itself behaves in very peculiar ways. If you could get near a black hole, you would find that time for you slows down dramatically compared to the rest of the universe, presenting a reality that truly challenges the imagination. Einstein's theory of relativity presents a remarkable concept. Your very experience of time can be altered by gravity. This means if you were in one place and your friend was in a distant location with a different gravitational field, time would genuinely pass at different speeds for both of you. Black holes also introduce a profound enigma known as the information paradox. For decades, this question has perplexed physicists. What happens to the information contained within matter after a black hole destroys it? The challenge has forced a complete rethinking of our most fundamental ideas about the universe's nature. It's conceivable that black holes are not the ultimate endpoints we imagine them to be. Instead of obliterating information, perhaps they transform it in some unknown way. The pursuit of these answers is a thrilling and constantly evolving scientific journey, as researchers develop new theories and experiments to probe the function of black holes within the cosmos. Every new insight we gain brings us a step closer to deciphering the secrets of these mysterious phenomena. When you gaze at the night sky, you might contemplate how many black holes reside in our galaxy. The answer is astoundingly high, with estimates suggesting millions exist, the great majority of which are completely invisible to us. Yet, their gravitational influence is deeply felt in the intricate dance of the stars and the overall architecture of our galaxy. In a sense, by observing the stars, you are also witnessing the effects of these hidden giants. Black holes stand as one of the true wonders of the universe, compelling you to reflect on the very nature of reality, gravity, and time itself. As our exploration of the cosmos advances, each discovery about these enigmatic objects enhances our understanding of humanity's place in this vast universe. So, the next time you find yourself looking up at the sky, remember that although you cannot see them, black holes are out there, their secrets waiting to be discovered like pages in an ancient book we have only just begun to read. Gravity is a pervasive force that shapes every corner of the universe. But have you ever considered how it sculpts entire galaxies? Its role extends far beyond keeping planets in orbit. Gravity is the central force behind the formation and evolution of galaxies. You can picture each galaxy as a vast cosmic garden, with stars as the flowers, and gravity as the gardener that organizes and maintains the entire system. When you observe the expansive universe, you can easily perceive gravity as the universal thread that binds everything together. Galaxies, each made up of billions of stars, owe their very existence to gravitational attraction. In the universe's infancy after the Big Bang, Minor fluctuations in the density of matter allowed gravity to begin pulling more material together. Much like a magnet gathers iron filings, gravity slowly amassed particles, giving rise to the first stars and eventually the galaxies we observe today. Galaxies are not static entities. They are dynamic systems that are constantly in motion and evolving, with gravity serving as the architect of their structure. For example, the extended arms of spiral galaxies like the Milky Way are a consequence of rotation, with gravity holding the stars in their orbits to preserve this distinct form. Elliptical galaxies, in contrast, have a smoother, more rounded shape, which is the outcome of gravitational mergers between smaller galaxies over billions of years. It's truly astonishing to consider that gravity dictates not only a galaxy's shape, but also its ultimate fate. Galaxies can collide and merge in a process that spans billions of years, much like two rivers converging to form new currents. During these collisions, gravity is the key force that redistributes stars and gas, often sparking the birth of new stars amidst the upheaval and acting as an engine of cosmic renewal. However, not all gravitational encounters are constructive. The intense gravitational interactions between some galaxies can trigger the formation of supermassive black holes at their cores. When two galaxies venture too close, gravity can disrupt their structures, forcing material to accumulate at the center, and sometimes creating a black hole. This central black hole can then start to feed on its surroundings, establishing a cycle that profoundly alters the galaxy's future. Within the grand scale of our expanding universe, gravity plays another compelling role. While the cosmic expansion drives galaxies apart, gravity acts as an opposing, attractive force that could theoretically slow this process and even initiate a universal contraction. Yet, current observations indicate the expansion is accelerating, a finding that has given rise to the concept of dark energy, a mysterious force that appears to counteract gravity's pull. The investigation into gravity's effect on galaxies is not solely based on observation. Astronomers employ sophisticated computer simulations to model the evolution of galaxies, which helps them better comprehend the complex cosmic processes at work. These simulations enable scientists to explore scenarios that cannot be observed directly, offering deeper insights into how gravity has guided the formation and movement of galaxies over time. Looking toward the future, the connection between gravity and galaxies remains a major focus of research. With the arrival of new technologies like the James Webb Space Telescope, scientists anticipate capturing more detailed images of distant galaxies and their evolutionary paths. This new stream of information promises to reveal long-held secrets about the history of the universe and its magnificent large-scale structure. The endeavor to comprehend gravity and its influence on galaxies naturally guides us toward more profound cosmic inquiries. Are there countless more galaxies beyond our current view? And how does gravity shape the potential for life in those remote parts of the universe? Each new insight adds another page to our celestial story, with gravity consistently serving as a central element of this grand narrative. The universe's magnificence is found in its intricate nature and the countless interactions unfolding on every scale. Gravity, a force you might think of as simple and familiar, is actually a deeply mysterious phenomenon that provides a key to understanding the vast cosmic web. From the birth of galaxies to their ongoing transformation, gravity presents a unique viewpoint into the universe's secrets, serving as a reminder that despite our smallness, we are fundamentally connected to everything. Gravity is a remarkable force that not only anchors you to the Earth but also dictates the very structure and evolution of the cosmos. But what if I were to tell you that this familiar force is intertwined with one of the most enigmatic energies in existence? Let's delve into dark energy, the mysterious influence that seems to be speeding up the expansion of the universe.
To visualize this, think of a balloon being inflated. In the beginning, its surface is compact, but as more air fills it, different points on the surface stretch away from one another. This provides a solid analogy for the expansion of space itself. The truly astounding part, however, is that this expansion isn't just happening. It's accelerating. The reason for this acceleration is where dark energy enters the picture. Dark energy is believed to constitute roughly 70% of the universe's total contents. But what is it exactly? It behaves like an anti-gravitational force, actively pushing galaxies apart and propelling them away from each other at an ever-increasing rate. So, how does this directly relate to the force of gravity that you know? To grasp their relationship, you must remember that gravity is fundamentally an attractive force. Consider how Earth's gravity holds you firmly in place. Dark energy, however, appears to be in direct opposition to gravity, generating a repulsive push that counteracts gravitational pull. If you imagine gravity as a powerful magnet drawing things together, then dark energy is like a leaf blower forcefully scattering them in every direction. This cosmic tug-of-war between gravity and dark energy is what sculpts the large-scale structure of the universe and determines its evolution. Scientists are constantly exploring questions like what would happen if gravity were stronger, and whether it could ever overpower dark energy. In their search for answers, astrophysicists have turned their attention to supernovae, the cataclysmic explosions of massive stars which are so brilliant they can be observed from immense distances. By analyzing the light from these distant stellar explosions, scientists have successfully measured the rate of the universe's expansion. They were shocked to discover that space is not just expanding, but is doing so more rapidly than all previous models predicted. This finding led them to the unavoidable conclusion that some unknown force must be driving everything outward, and we have named that force dark energy. The implications of this discovery are far-reaching, as dark energy might also determine the ultimate destiny of our universe. If it continues to accelerate cosmic expansion, a time could come when all other galaxies are so far away they become completely invisible to us. Picture an infinite ocean of darkness, where stars and galaxies are so remote that their light can never reach us. This is one possible future for our cosmos, a fate potentially sealed by the persistent influence of dark energy. The precise connection between gravity and dark energy remains a profound puzzle that we have yet to solve. Some scientists propose that gravity might actually be weaker over vast cosmological distances because of dark energy's influence. Other theories speculate that we could be witnessing the effects of entirely new physical laws that we currently do not comprehend. This raises another fascinating question. Could there be different forms of dark energy still waiting to be found? As our telescopes become more powerful and our technology advances, researchers are relentlessly seeking new methods to unravel these cosmic mysteries. The future of research into gravity and dark energy promises to open new frontiers in our perception of the cosmos. Contemplating these forces compels you to think about the fundamental nature of reality itself. If gravity is the cosmic glue holding us together, what does that signify in a universe that is constantly expanding? Are we fated to stay bound together in this immense cosmos? Or will everything eventually drift apart, leaving us as isolated islands of matter in an empty void? Every new piece of the puzzle we uncover about dark energy and its relationship with gravity brings us one step closer to finding out. Human curiosity is a relentless engine, with each new revelation prompting us to ask even more questions.
What awaits us beyond our current knowledge? And what other secrets is the universe hiding? The quest for understanding is an unending journey, and forces like gravity and dark energy remind us there will always be more to learn, from our home on Earth to the farthest reaches of space. Every step you take on this path brings you closer to a deeper comprehension of our shared reality. So, the next time you gaze upon the night sky, remember that you are witnessing not just stars, but a cosmos in constant flux, where gravity and dark energy perform a delicate and powerful dance.
Quantum gravity is a subject that captivates many, and with very good reason. How is it possible to reconcile the colossal force that governs planets and stars with the bizarre and fascinating domain of subatomic particles? This profound challenge has spurred physicists worldwide to hunt for answers that could revolutionize our entire model of the universe. Gravity, as you typically understand it, is a force that operates between objects with mass. Yet quantum mechanics functions in a realm where the established rules no longer apply. Imagine a reality where particles behave like players on a soccer field, but instead of adhering to predictable patterns, they often act in ways that are entirely random. The core of the quantum gravity problem lies in figuring out how to unite this quantum uncertainty with the dependable stability of the gravity that keeps you grounded. Quantum gravity stands as an intriguing area of research dedicated to solving one of modern physics' greatest puzzles. How is it possible for two incredibly successful theories, quantum mechanics and general relativity, to be fundamentally incompatible, despite describing our universe at vastly different scales? You can think of it as having two brilliant friends who simply cannot get along. General relativity governs the behavior of massive objects in space, while quantum mechanics delves into the microscopic realm, where subatomic particles engage in a dance of probabilities. At the heart of this challenge is the notion that gravity might be something far more fundamental than a mere force. While classical Newtonian physics describes gravity as a mutual attraction between objects with mass, the quantum perspective is investigating whether gravity is actually an outcome of spacetime's geometry. You can picture space and time as an immense fabric. Massive objects cause dips in this fabric, which in turn guide the motion of other objects, much like marbles rolling on a stretched net. This view suggests gravity is more about the universe's shape than a force acting across a distance. One of the most prominent attempts to bridge the gap between gravity and quantum mechanics is known as string theory. This theory posits that the basic constituents of the universe are not point-like particles, but rather minuscule, vibrating strings. The specific manner in which these strings oscillate determines the type of particle they manifest as. The question then arises, could gravity itself be explained by the interactions of these strings? If so, it would not only revolutionize our understanding of gravity, but also potentially unify all the fundamental forces of nature, although string theory currently lacks definitive experimental proof. An alternative perspective is offered by the concept of emergent gravity. Within this model, gravity is not a fundamental property of nature, but instead arises from more elementary interactions among particles. It's as if gravity is a large-scale phenomenon that appears from the collective behavior of countless tiny components, similar to how the sensation of temperature emerges from the kinetic energy of individual atoms. While this idea may seem unconventional, it exemplifies how scientists are pushing beyond traditional frameworks to resolve the enigma of gravity. This pursuit naturally leads to a profound question. How can we possibly observe and measure gravity within a quantum framework? Experiments aiming to probe quantum gravity are extraordinarily complex and demand the most advanced technology available. Among the most promising techniques is quantum interferometry, which enables researchers to see how particles behave when influenced by gravity. Such experiments could offer vital clues about the true nature of gravity at the smallest possible scales. Beyond the scientific pursuit, the quest for quantum gravity also brings forth significant ethical and philosophical questions. If we ever manage to unify gravity with quantum mechanics, how might that discovery reshape our view of the universe and our place within it? The concept that everything is intricately linked through particles and forces can be both awe-inspiring and bewildering, compelling us to reflect on our relationship with the cosmos. This isn't just a puzzle for theoretical physicists. It's a journey that touches upon the very essence of our existence. Moreover, the future of technology could be profoundly affected by this research. Could a deep understanding of gravity at the quantum level unlock new innovations, perhaps even devices that can manipulate this force in ways we can't yet conceive? In the same way that harnessing electricity completely transformed human society, mastering quantum gravity could usher in a new era for science and technology. The potential is immense, opening a new chapter in our history. Ultimately, the future of quantum gravity research is a thrilling expanse of possibilities. As scientists venture deeper into this uncharted territory, each new experiment and every theoretical breakthrough brings us another step closer to solving the mysteries of this fundamental force. The quest to unify gravity within quantum terms is more than a scientific challenge. It is an odyssey that invites us all to reimagine our understanding of the universe, leaving us to wonder what incredible discoveries lie just over the horizon. Loop quantum gravity offers an alternative perspective, envisioning space and time as a vast grid of incredibly small, indivisible units. You can picture it like a cosmic chessboard, where every square constitutes a fundamental piece of space-time, suggesting that gravity isn't a smooth, continuous force, but rather operates on a granular level. But the crucial question is, how could we ever confirm if such a network is real? The path to an answer is through experimentation, although trying to measure gravity at the quantum scale presents an immense challenge. For instance, scientists are working to detect gravitational waves, which are faint ripples in space-time generated by colossal events like the collision of black holes. Isolating these waves is an intricate task, akin to hearing a single whisper within a roaring crowd, and it demands extraordinarily sensitive technology. Among the most ambitious endeavors in this domain is the Laser Interferometer Gravitational Wave Observatory, or LIGO, which has already successfully detected these waves. This achievement not only validated Einstein's theory, but also unlocked a new set of inquiries, prompting us to wonder if we might one day witness quantum gravity in action. However, the search isn't limited to passively observing cosmic events. Other experiments are being designed to actively create environments where quantum gravity might just reveal itself. Some researchers employ atoms cooled to near absolute zero, observing their behavior in circumstances that defy our current models of gravity, effectively turning their labs into miniature cosmic testbeds to probe the universe's fundamental rules. Consider the possibility that quantum gravity holds profound implications for our entire conception of the cosmos. Imagine that the gravity you experience is merely the visible part of a much larger, hidden reality. If we could successfully merge gravity with quantum mechanics, it might expose the secrets of the universe's creation, or even hint at what exists beyond its boundaries. Naturally, the pursuit of quantum gravity brings up a host of philosophical dilemmas. If space and time are fundamentally discrete, does that mean the reality you perceive is profoundly different from what it actually is? Are we perhaps living within an illusion constructed by the limits of our own senses? These inquiries might appear abstract, but they are precisely what fuels our innate human drive for discovery.
Some scientists even propose that a true understanding of quantum gravity could lead us to answers about the very nature of consciousness and existence. Could it be that by studying gravity at its most fundamental level, we are also probing the frontiers of the human mind? While it may sound like a significant leap, science and philosophy have a history of intersecting in the most unexpected ways.
In the meantime, the global scientific community is relentlessly advancing its efforts. A multitude of projects are underway worldwide, spanning everything from laboratory-based experiments to vast astronomical observations, all with the goal of illuminating this enigmatic crossroads of gravity and quantum mechanics. This search is an intense and thrilling journey, where each minor breakthrough brings us closer to unraveling one of the universe's most profound enigmas. So the next time you consider the force of gravity, I want you to remember that a whole universe of discoveries is still out there, waiting. Quantum gravity is more than just a theoretical discipline. It is a lens offering new ways to comprehend the cosmos. It invites you to challenge what you believe you know, and to venture into the vast unknown, as the story of gravity is far from complete, with new chapters being added to this cosmic narrative every single day.
Gravity is a force that accompanies you through every moment of your existence. But what if I told you that not all gravitational forces are created equal? Here on our own planet, gravity appears to be a constant. Yet as we examine other celestial objects, an incredible diversity becomes apparent. I want to explore how gravity differs on other planets, and what consequences this has for life and the potential for human colonization.
Let's start with Earth, where gravity is the very thing that keeps your feet planted on the ground. If you jump, you are certain you will return. But what would you experience on other worlds? Each planet possesses a unique size and mass, which means the gravitational force it generates also changes. On Mars, for example, which is considerably smaller than Earth, gravity is only about 38% of what we feel, meaning you could leap nearly 3 times higher than you can here.
Now, let's turn our attention to Jupiter, a gas giant with a mass over 200 times that of our planet. The gravitational pull at its surface is so immense that a person's weight would more than double. This wouldn't just hamper your ability to move, it would also lead to severe health issues. Try to imagine living in a place where every single step demands more than twice the effort. It would present a truly formidable challenge. Yet, gravity's influence extends far beyond just human beings, as the life you see around you has evolved within a very specific gravitational setting. On worlds with different gravitational forces, it's conceivable that entirely different life forms could arise, uniquely adapted to those local conditions. Plants, for instance, might develop in very strange ways. In a lower gravity environment, trees could soar to unbelievable heights without the same structural stress on their trunks. Another compelling consideration is how gravity shapes the behavior of water and other liquids. On a planet with weaker gravity, water might move in unfamiliar patterns, giving oceans, lakes, and rivers truly distinct characteristics. You could imagine an ocean where gentle currents drift slowly in place of crashing waves, as if performing a dance to a subtle melody, which would in turn have a deep effect on the climate and the evolution of life. Gravity is also a decisive factor in the logistics of establishing human colonies on other worlds. Should we ever commit to building a permanent base on Mars, we would have to confront numerous challenges. The reduced gravity could impact not just our physical well-being, but also the very methods we use for constructing shelters and cultivating food. Any environment with a different gravitational pull would necessitate significant innovations in both technology and architectural philosophy. And what about the smaller bodies in our solar system, such as dwarf planets and asteroids?
On these minor celestial objects, the force of gravity is so faint that it may be insufficient to hold on to an atmosphere. This lack of a gaseous envelope exposes their surfaces directly to the harshness of space, creating environments that are fundamentally different from anything you would experience on a larger planet. This implies the absence of liquid water, which is an essential prerequisite for life as we understand it. On an asteroid, you could leap into the air and drift about as though you were in a weightless theme park. But could such a location ever be genuinely habitable? Furthermore, gravity dictates the way planets spin and travel around the sun, with each celestial object possessing the unique gravitational path that charts its course and its interplay with other worlds. These gravitational relationships between celestial bodies can trigger the creation of rings, such as those encircling Saturn, or even lead to the formation of moons. Have you ever let your mind wander to what it would be like to live on the moon? It's possible that in the years to come, we will witness the establishment of human settlements on these other worlds. Space missions have provided scientists with the opportunity to examine how gravity impacts astronauts. Aboard the International Space Station, crew members exist in a microgravity environment where they feel weightless. This experience offers insights into what life could be like on other planets and how we might acclimate to such different gravitational forces. What might unfold if our species were to adapt to an existence in an environment with a different gravitational pull? The potential outcomes are truly limitless. We should also remember that investigating gravity on other planets deepens the understanding of our own world. By contrasting Earth's gravity with that of other cosmic bodies, scientists can uncover more about our planet's history and its evolutionary path. Each new finding brings us a step nearer to solving the universe's great puzzles. In essence, the subject of gravity on other planets not only ignites our curiosity, but also dares us to envision a future where humanity could inhabit and prosper on different worlds. The variance in gravity could profoundly shape life, technology, and the course of space exploration. As we venture out into the cosmos, every fresh discovery about gravity provides a new vantage point on our own place within it. What marvels might await us in the future as we continue our quest for other habitable planets? And what exactly are gravitational waves, and why are they so crucial for comprehending our universe? Picture space-time as a vast, flexible sheet. If you set a heavy object on it, like a bowling ball, the surface warps. Now, if you roll a marble close to that indentation, you'll notice it curves toward the bowling ball, not from a direct attraction, but because the fabric of space-time itself is bent. This is a foundational idea for grasping how gravitational waves operate across the cosmos. Gravitational waves are ripples in the very structure of space-time, generated by the accelerated motion of extremely massive objects, such as a pair of black holes spiraling into one another and ultimately merging. This is an event of immense scale, akin to two colossal vortices colliding in a cosmic sea. The energy unleashed from this fusion sends waves propagating through the universe at the speed of light, enabling us, for the first time, to actually hear cosmic phenomena we could previously only witness with light. Are you aware that the first successful detection of gravitational waves was announced in 2015? This was a landmark achievement, on par with the invention of the radio or the first use of the telescope. The Laser Interferometer Gravitational Wave Observatory Collaboration, known as LIGO, which operates 2 facilities in the United States, captured these ripples, thereby validating a prediction Albert Einstein made within his theory of general relativity. The sheer excitement of the scientists involved was undeniable, as they had not only proven a century-old theory, but it also unlocked a completely new method for observing the universe. This naturally leads to the question,
What can these waves teach us? Gravitational waves present a novel way to perceive the cosmos, distinct from what light reveals. While telescopes let us see things that emit or reflect light, gravitational waves inform us about events that are often entirely concealed from our view. They narrate the tales of colliding black holes, exploding supernovae, and the birth of stars, giving us a way to investigate phenomena that were once completely invisible. Consider this. When a giant star detonates in a supernova, it doesn't just radiate brilliant light. It also produces gravitational waves that spread across space. If we possessed a microphone with enough sensitivity, we could pick up the echo of that cataclysm from thousands of light years away. This capability allows us to explore the origins and evolution of stars in ways previously unimaginable. The significance of detecting gravitational waves extends far beyond simple scientific inquiry. These waves serve as a new instrument for putting general relativity to the test. When they are detected, scientists are able to compare theoretical models with observed reality, which helps us to sharpen our comprehension of gravity. It's as if we've been given a fresh set of rules to understand physics, where every detection is a new play that reveals more about the game of the universe. As our technology progresses, new observatories are slated for development that will be capable of capturing gravitational waves across a wider range of frequencies. This suggests that in the future, we could learn about even more remote and powerful cosmic events. Imagine being able to listen to the grand symphony of the universe, where each collision and every event contributes a note to a celestial melody. Of course, achieving this is anything but simple. Gravitational waves are extraordinarily faint, demanding technology of extreme sensitivity for their detection. Facilities like LIGO and its successors are engineered with precision down to the millimeter to catch these minuscule vibrations in space. The challenge is comparable to trying to hear the sound of a single leaf falling in the middle of a raging storm. The discovery of gravitational waves also opens up a host of new questions. What other cosmic events might be generating waves that we have yet to find? What secrets does the universe conceal within its most obscure regions? These inquiries are now the focus of intense research within the scientific community, and each subsequent detection holds the promise of advancing our understanding even further. Among the most compelling qualities of gravitational waves is their profound link to black holes. An immense surge of energy, comparable to that of billions of suns erupting at once, is unleashed when two black holes collide and merge. Each time we detect such an event, it not only reconfirms the reality of these enigmatic cosmic bodies, but also enriches our knowledge of gravity's fundamental nature. When you pause to consider the larger meaning, it becomes evident that gravitational waves are far more than a new scientific curiosity. They provide an entirely different method for engaging with the cosmos. These ripples in space-time show us that reality has many more layers than we typically perceive, beckoning us to explore and challenge our current understanding. As scientific knowledge advances, these waves open up a thrilling avenue into the future, serving as a constant reminder that our universe is a dynamic, ever-evolving place filled with wonders yet to be found. Have you ever wondered what your life would be like without gravity? It's a concept so ingrained in our daily existence that we seldom give it a second thought. Yet our comprehension of this fundamental force has been the bedrock of modern technology. From the simple mechanics of walking to the astonishing accuracy of satellite navigation, gravity is the silent partner in these achievements, and without it, our everyday reality would be unrecognizably altered. Take the Global Positioning System, or GPS, which most of us use simply to find our way. You might be surprised to learn that its very operation hinges on gravity. The satellites circling our planet are traveling at incredible speeds and great heights,
causing them to experience time dilation, as predicted by Einstein's theory of relativity. This means their internal clocks run at a different rate than ours on Earth, and if this gravitational effect weren't precisely calculated, your GPS could easily misdirect you, leading to serious complications. Beyond navigation, satellite technology is also indispensable for meteorology. The images and data that satellites gather about our planet's atmosphere are entirely dependent on gravity holding them in their exact orbits. Lacking a sophisticated grasp of how gravity functions, our ability to forecast storms, hurricanes, or shifts in climate would be severely compromised. In this way, gravity not only shapes our lives, but is also a critical tool for protecting them. Even the smartphone you carry everywhere relies on gravity. These devices contain tiny sensors called accelerometers, which are responsible for detecting the phone's orientation in space. If you've ever marveled at how your screen seamlessly shifts from portrait to landscape mode as you turn it, you've witnessed a process directly connected to how those sensors interpret the pull of gravity. Our modern devices simply wouldn't work as they do in its absence. Furthermore, gravity profoundly influences the development of our communication infrastructure. Radio waves and other signal types are all affected by Earth's gravitational field. For instance, successfully transmitting a signal from a satellite back to Earth demands a precise calculation of how gravity will bend the signal's path. Without this knowledge, contemporary conveniences like international video calls or music streaming services would not be feasible. In the realm of space exploration, gravity's role is absolutely central. When a spacecraft is sent into the cosmos, it must harness gravity to establish a stable orbit. Engineers employ a technique called a gravitational assist, often known as a slingshot maneuver, which uses a planet's gravitational pull to accelerate a craft. This method is vital for interplanetary missions, as it enables us to save fuel and reduce travel time, pushing human and robotic exploration further into our solar system. Medicine has also reaped benefits from our knowledge of gravity. Technologies like magnetic resonance imaging, or MRI, which are commonplace in hospitals, operate based on principles involving magnetic fields and gravitational forces. Meanwhile, researchers continue to explore new ways to leverage gravity for better diagnostics and therapies. Observing the profound physiological changes astronauts undergo in zero gravity also provides invaluable insights into human health. Gravity's influence extends into the world of sports, where coaches and athletes meticulously study its effects on physical prowess. From the arc of a soccer ball to the execution of a gymnastic routine, a deep understanding of this force allows athletes to maximize their performance and minimize injury risks. The entertainment industry similarly draws upon our knowledge of gravity, using it to simulate realistic special effects in films and video games, from massive explosions to thrilling acrobatic feats, which creates more believable and immersive experiences for you. Looking ahead, research into gravity continues to push the boundaries of what's possible. It's a force so fundamental that we often overlook its colossal impact on our world. From the technology in our hands to the exploration of distant planets, our understanding of gravity is woven into the very fabric of modern life, silently enabling the world you know today. Have you ever paused to consider how this essential force was the very key to life developing on our planet? Gravity has been a constant presence since Earth's formation, sculpting not just its physical structure, but also steering the evolutionary path of every species to ever inhabit this world. When you examine the concept of life, gravity proves to be a deciding factor in everything, from the way a plant grows to the fundamental development of all organisms. Picture a seed as it settles into the soil. Gravity does more than just pull it down. It actively directs its growth. This force dictates the precise direction for the root to tunnel into the earth and for the stem to reach toward the sunlight. Without gravity's guidance, roots would have no sense of direction, and plants might simply drift about, meaning the lush and varied vegetation that blankets our world today would be entirely absent. As life continued to evolve, gravity's influence extended to the development of animals. Creatures dwelling in the oceans, for instance, had to adapt to both water pressure and the planet's gravitational pull. A far greater challenge, however, awaited those animals that chose to leave the water and claim the land. Gravity forced their bones and muscles to evolve, becoming strong enough to support their own body weight and move with efficiency. It's clear that without gravity, the entire trajectory of vertebrate evolution would have been profoundly different. It's possible they might never have come to be. Turning to our own story, gravity has deeply shaped how the human species adapted to the world. We evolved into bipedal creatures, which means we walk on two legs in an upright posture. This stance wasn't just advantageous for seeing farther or traveling efficiently. It was a direct evolutionary answer to gravity. Our bones and joints developed a unique structure capable of bearing this constant force, allowing us to move with a distinct combination of grace and agility. Just try to imagine existence within a different gravitational field. On the moon, for example, the gravitational pull is merely 1/6 of what you feel on Earth. A simple jump that brings you back down almost instantly here would let you float through the air for a much longer time there. If humans were to establish a permanent settlement on the moon, our bodies would have to undergo profound adaptations, as the weaker gravity would alter bone density and muscle mass, compelling us to embrace a completely new way of living. Gravity's role extends far beyond merely anchoring us to the ground. It is also the regulator of our planet's water cycle and climate. Without its pull, water wouldn't be contained within oceans, rivers, and lakes, which means the fresh water so crucial for life would be non-existent. This force enables water to travel from one location to another, driving the cycle that is absolutely essential for every terrestrial ecosystem. The rain that falls and the rivers that flow are all consequences of gravity pulling water toward the Earth's core. Within the realm of biology, gravity even influences how our bodies process nutrients. It directly impacts your circulation, as your heart is engineered to pump blood against its constant downward force to supply every part of your body. If you were to find yourself in a microgravity environment, like aboard a spacecraft, you would quickly realize your body operates differently. Astronauts in space famously contend with physical transformations, including a loss of muscle mass and bone density, all because of gravity's absence. This fundamental force has also been a major consideration in our exploration of space. As scientists and astronauts map out plans for colonies on other planets, they must carefully calculate how different gravitational forces will impact human life. On Mars, gravity is approximately 1/3 of what we experience on Earth. This reality suggests that humans would need to engineer specialized technologies and habitats to properly adapt, ensuring they can not only survive, but also flourish under such different conditions. Furthermore, gravity is a critical variable in the ongoing search for life beyond Earth. Scientists carefully assess how a planet's gravity might influence its potential for hosting liquid water, which is a non-negotiable ingredient for life as we understand it. Consequently, whenever a new exoplanet is located, its gravitational pull is one of the very first characteristics to be analyzed, as it offers vital clues about the world's capacity to support life. When you take all of these influences into account, it becomes strikingly clear that gravity is so much more than the force that keeps your feet on the ground. It is the architectural element that has molded life's evolution on this planet, shaping our interaction with the environment, the growth of plants, the development of animals, and our own adaptation. Every aspect of life is woven into this invisible force, from the rhythmic movement of the tides to the effortless flight of a bird, making life itself a testament to the beautiful interplay between gravity and evolution. Lacking this force, the entire history of life on Earth would have unfolded in a completely different way, and it's quite possible we wouldn't be here at all. For all its complexity, gravity is the simple thread that binds all life together, connecting every living thing across this immense universe. So, what do we truly understand about it? Many people just see it as the reason things fall down. But what if I were to tell you that there's a great deal more to the story? A number of myths have grown around this foundational cosmic phenomenon, and I think it's time we started to unravel them. First, let's tackle the notion that gravity is a force that operates exclusively on Earth. Although its effects are certainly more pronounced for us here, gravity is in fact everywhere. The instant you walk outside, you are not only subject to Earth's gravitational pull, but are also being influenced by the gravity of the Sun and every other celestial object in the cosmos. Gravity recognizes no frontiers. Its reach is infinite, linking together everything in existence. Another widespread myth is the belief that gravity is a constant. Some people assume the gravitational force we experience on our planet is the universal standard, but that simply isn't accurate. The strength of gravity is highly variable and depends entirely on the celestial body you happen to be standing on. To give you a clear example, the gravity on the Moon is only 1/6 as powerful as it is here on Earth. Most people associate gravity with the simple act of an object falling. But suppose I were to tell you that this force is far more complex. Numerous myths and misunderstandings have grown around this fundamental universal principle over time. So let's start by dispelling a few of the most common ones. To begin, let's tackle the notion that gravity is exclusive to our planet. Although we certainly experience its pull most strongly right here, this force is actually ubiquitous. The moment you walk outdoors, you're not only subject to Earth's gravitational field, but also to the subtle pull of the Sun and countless other cosmic bodies. Gravity is a limitless force that permeates the entire cosmos, binding together all of existence. Another widespread misconception is that gravity is a constant force throughout the universe. Many assume the gravitational pull we feel on Earth is a universal standard. But the intensity of gravity actually changes depending on which celestial body you're on. On the Moon, for example, its strength is merely 1/6 that of Earth's, meaning if you weigh 60 kilograms here, you would only weigh 10 kilograms there. Just think about the incredible physical feats you could accomplish with so little weight holding you down. People also mistakenly believe that an object's size directly determines its gravitational strength. While a huge planet obviously has more gravitational influence than a small stone, an object's density is just as crucial as its dimensions. An incredibly dense but small body, like a neutron star, can generate a truly staggering gravitational field, proving that with gravity, appearances can be quite misleading. This brings us to the frequent confusion between mass and weight, two terms people often use as if they mean the same thing. Your mass refers to the actual amount of matter you are made of, and this value remains constant anywhere in the universe. Your weight, however, is the measurement of gravity's pull on that mass, which is why in a low-gravity setting like the Moon, you would weigh significantly less, even though your mass hasn't changed at all. So, what about the idea of gravity in space? Perhaps the most pervasive myth is that space is a zero-gravity environment, which is fundamentally untrue. Gravity is absolutely active in space,
It's the very force that holds planets in their solar orbits and locks moons in orbit around those planets. The weightlessness astronauts feel aboard the International Space Station isn't due to a lack of gravity, but because they are in a continuous state of freefall.
It's also a mistake to think gravity only influences large-scale objects. The reality is that this force acts on everything, right down to the subatomic level, affecting molecules and atoms, even if its impact at that scale is minuscule. This universal principle acts on all matter, meaning that the very atoms composing your body are interconnected by this incredible, pervasive force. Let's consider the old saying, "What goes up must come down." This certainly holds true for things we toss into the air on Earth, but it is not a universal law. Out in the vacuum of space, an object can travel on its trajectory forever, provided no other force intervenes to alter its path. So, where does this leave our understanding of gravity? For centuries, it has remained one of science's great enigmas, and despite our remarkable progress, vast areas of it are still uncharted territory. Human curiosity is boundless, and with every cosmic secret we manage to unlock, a host of new questions emerges, compelling us to push our exploration even further. The force that anchors you to the Earth, gravity, represents merely the surface of a vast ocean of undiscovered knowledge. Perhaps the most compelling puzzle in physics is the quest to unite gravity with nature's other fundamental forces. Science currently recognizes four such forces: gravity, electromagnetism, and the strong and weak nuclear forces. While the last three are elegantly described by quantum mechanics, gravity remains the outlier, like a single puzzle piece that refuses to fit into the grand picture. This fundamental difference in behavior leaves us grappling with how to merge these distinct forces into a single, cohesive theory. Researchers are developing concepts like quantum gravity, which aims to express the force of gravity using the language of quantum mechanics. To grasp this idea, consider how gravity governs massive objects like planets and stars, while quantum mechanics dictates the strange rules of the subatomic realm. Quantum gravity, therefore, acts as a theoretical bridge, seeking to connect these two seemingly incompatible worlds. A promising avenue for this unification is string theory. This model proposes that the fundamental constituents of the universe are not point-like particles, but minuscule vibrating filaments of energy. According to this theory, each unique particle is simply the result of a string vibrating in a different pattern. This elegant concept not only provides a potential pathway to unifying all forces, gravity included, but also intriguingly hints at the existence of dimensions beyond the three you experience every day. Beyond pure theory, scientists are also conducting experiments to measure gravity's influence at the quantum level. A particularly exciting technique is quantum interferometers, which leverages light to investigate how quantum phenomena might interact with the gravitational force. Through the use of sophisticated technologies, researchers aim to witness gravity's impact on particles existing in a quantum state. The results of this work could reveal if gravity operates by different rules on the smallest scales, potentially unlocking a new chapter in our understanding. Shifting our view to the cosmos, the study of gravity on other planets and celestial bodies presents its own set of questions. Our exploration of space has enabled us to measure gravitational fields in diverse environments, from Mars to the massive gas giants. Every world possesses a unique gravitational signature, and comprehending these variations is vital for the success of future missions, whether for exploration or colonization. For instance, you must consider how the reduced gravity on Mars will impact the health and development of future human inhabitants. We must also consider gravity's role in the universe's most extreme phenomena, particularly black holes.
As researchers delve into these cosmic mysteries, they confront how gravity can create conditions that defy our conventional understanding of space and time. When you examine the physics of black holes, it becomes apparent that gravity's effects can become so profound that time itself is warped. The secrets concealed within these dark behemoths might just revolutionize your perception of the entire cosmos.
On the grandest scale, gravity is a key player in the expansion of the universe itself. It exists in a delicate cosmic balance with dark energy, an enigmatic force that appears to be accelerating this expansion. The very existence of this opposing energy raises profound questions about the ultimate fate of the universe. Consequently, investigating dark energy and its interplay with gravity is crucial for comprehending how the cosmos has evolved and where it is headed. With every fresh discovery, researchers must re-evaluate established theories and pursue more profound answers, because gravity continues to be a puzzle that generates more questions than solutions. This enduring mystery is precisely what fuels the engine of scientific curiosity. It leads you to wonder not only about the physical nature of gravity, but also about its influence on your philosophical perspective of the universe. Each breakthrough forces you to contemplate your place in the cosmos, making the quest to understand gravity a journey toward understanding yourself. Looking ahead, gravity promises to remain a thrilling field of research, rich with unsolved problems and ripe for discovery. As our scientific capabilities grow, so too must your comprehension, fueled by the relentless curiosity that compels us to venture into the unknown. This fundamental force links you not just to our planet, but to the boundless universe beyond. Every advance in its study brings you closer to a deeper appreciation of your role in the cosmic drama, an adventure that is only just getting started. While you experience gravity as the invisible pull that holds you to the ground, it is fundamentally more than a simple attraction between objects. It acts as the grand conductor of the cosmos, orchestrating the motion of everything from small pebbles to immense galaxies. This force is so critical that it shapes the very environment you live in. Without it, neither the planets nor the stars that illuminate the night sky could ever have formed. Humanity's effort to comprehend this captivating force stretches across history, from the early Greek philosophers pondering celestial motion to the transformative insights of Isaac Newton and Albert Einstein. Every milestone has brought us closer to solving a riddle that has enchanted thinkers for ages. It is remarkable to consider that the simple sight of an apple falling from a tree could spark such deep contemplation about the universe's mechanics, leading Newton to formulate his law of universal gravitation, which states that every object exerts a pull on every other. This very concept completely reshaped science, giving us the ability to forecast the orbits of planets with breathtaking accuracy. But what unfolds when you explore the domain of extreme velocities and truly massive objects? The answer emerged from Einstein's theory of general relativity, which demonstrated that gravity is not some simple force, but an actual curvature of space and time itself. Can you picture a fabric that warps and sags when a heavy object is set upon it? That is an excellent analogy for how gravity operates on the structure of the universe. The consequences of grasping this idea are incredibly significant, leading to a complete reevaluation of the cosmos and our place within it. The idea that gravity can actually alter time sounds like a premise from a futuristic novel, but it is an undeniable fact of our universe. If you were to journey to the nearest star at the speed of light, you would find that time passes for you differently than for everyone back on Earth. It is remarkable to think that gravity can fundamentally change how we experience our lives and perceive reality. Moreover, the experiments that have validated these concepts are equally captivating. From the landmark Cavendish experiment, which first measured gravity with precision, to the recent detection of gravitational waves, every new discovery has brought us a step closer to solving the universe's greatest riddles. It's amazing to realize we can now detect ripples in space-time, almost as if we are listening to the melodies of the cosmos. Within our own solar system, gravity functions as the grand conductor of a cosmic orchestra, arranging the planets, their moons, and countless asteroids into a state of celestial balance. Without this fundamental force, Earth would lose its stable orbit, and the Moon would cease its perpetual dance around our world. Then there are black holes to consider. These perplexing areas of space, where gravity's pull is so immense that nothing can break free, stand as one of the most profound enigmas in modern physics. What kind of truths might they conceal within their shadowy depths? Gravity's influence extends far beyond our local neighborhood in space. It holds a crucial role in the creation and evolution of entire galaxies, dictating how they gather and transform over the course of billions of years. Have you ever considered how galaxies are born and the part gravity plays in that grand cosmic process? It is as if the universe is an intricate tapestry woven together by this invisible network of forces. The story of gravity does not stop there, as it is deeply connected with the puzzle of dark energy, the strange component that appears to be speeding up the expansion of the universe. How can a force so subtle and mysterious affect gravity and, by extension, the ultimate destiny of everything? This remains one of the most pressing questions that scientists are working to resolve. As we investigate gravity on the quantum scale, we are entering a domain filled with incredible potential and immense difficulties. The search for a unified theory that marries gravity with quantum mechanics represents one of the foremost challenges for contemporary physics. What kind of revelations await us on this expedition into the unknown? Every single experiment, whether simple or extraordinarily complex, has the potential to provide us with vital clues about how gravity truly functions at its most fundamental level. Comparing gravity on other planets and celestial bodies opens up an entirely new perspective on our universe. Imagine residing on a world where gravity is drastically stronger or weaker. How would that change life? And could we ever learn to adapt? Gravitational waves, which were only confirmed in the last decade, serve as a powerful testament to the might of this force. Like ripples spreading across a pond, these disturbances in the fabric of space-time provide us with an entirely new method for observing the cosmos. What further secrets are they destined to unveil to us in the coming years? Modern technologies, which have been developed thanks to our knowledge of gravity, have profoundly altered our way of life. From the global positioning system, or GPS, that guides our travels, to the satellites that connect our world, gravity is the unseen compass that directs so much of what we do. In the end, gravity is much more than a simple physical phenomenon. It is a critical ingredient for the development of life as we understand it. Without gravity's influence, Earth would not be the home that we know. The very possibility of life existing on other worlds may hinge on this force, compelling us to contemplate our own place in the vastness of space. So the next time you gaze up at the stars, remember that gravity does more than just keep your feet on the ground. It connects you to the boundless expanse of the cosmos. In this grand journey of discovery, each question we pose can unlock new answers, and every new answer can, in turn, lead to a universe of new questions. Gravity, at its core, serves as a constant reminder of just how magnificent and enigmatic our universe truly is.